very much. My name is Jung Lai. I'm from SKF Engineering Research Center. The subject I'm going to present is the effect of microstructure and surface roughness or surface finish on the fatigue strength of high-strength steels. This is also work with my co-workers, Hanjun Wang and Larsen. Okay, we know that high-strength steels is sensitive to defects, the various defects. So it depends on the type and the size. The defect may have a significant effect on the fatigue strength. We also know that this is well known, although it's a schematic SN curve. Sorry, go back. That for high-strength steels, and there are two distinct different mechanisms for failure. Surface initiation normally it occurs at relatively low cycles and higher stress, whereas the subsurface initiation characterized by fisheye that occurs at a relatively low stress but also extended to very high cycle fatigue. But also we know that so sometimes these two curves, you put them together, they mix, but it's also possible to offset that. If some effects such as stress concentration on the surface, then you will see the separation of these two mechanisms. But also that if we introduce surface defects like rough surface, and then also the surface initial will shift towards the shorter life. So the focus of this work is on the surface roughness. Well, existing approach to the surface roughness effect, including the engineering approach, actually that dated back to the 40s last century. Actually, then people just apply a kind of a surface reduction factor to the fatigue strength. And the various effects due to various heat treatment or surface treatment, the factors are determined experimentally. Like the one there, but that is still widely used. So there is also some modeling effort to try to understand the surface effect by means of notch effect, or treat the surface roughness as kind of surface defects, and then include that in the fatigue limit model, for example, by work of Murakami. Well, the objective of this work is to first categorize the effect of the surface finish on the fatigue strength, and based on that, we would like to develop a kind of description and to describe the effect on the fatigue strength. The material that we choose to study are actually the two types of the steel grade, both used for roller bearings. The first one is a high carbon chromium steel, and the other one is a medium carbon steel. So the first kind is more for through hardening, suitable because of the hardening ability. And the second one normally is you can use the surface hardening treatment. For the high carbon steel, we also heat treat that into different microstructure, granitic structure and the magnetic structure, and here are some details of the heat treatment. Whereas the low carbon steel, we do not heat treat that, so it's in the soft condition. I would like to point out that for magnetic steels, not only the magnetic structure but also include about 10% return oxide, whereas for the granitic steels, there is almost no or zero, very few return oxide. And also after heat treatment, you can see the hardness. For granitic is because 700, and magnetic is about a little bit higher, 780. And yeah, this is the medium carbon steel. And these are the experiments that we did. We use rotating bending testing. This is a testing machine. Frequency is 50 Hertz specimen. The size, minimum diameter is about 7 millimeter. After heat treatment, actually we treat the surface finish by using emery paper to different roughness. And according to the roughness levels, we can group it into different levels. We call it polished, rough 1, rough 2, and rough 3, rough 4. And here are the indication of the mean roughness levels for the different samples. Okay, let's look at the fracture surface fractography for different materials, but also different. So first look at the hardened steel, and we found doesn't matter is magnetic or magnetic steels, and the failure modes are very much similar. We see if for rough steel and mostly the crack initiation is from the surface. And you can see those initiating sites, so there is not just one, but also multiple sites on fracture surfaces. And if we zoom in, and you can see actually this is a big one, or probably the major one that causes fracture. And also you see that some small initiation sites, and even they are not on the same levels. And also on the side face, you can see also some multiple cracks actually occurs. And for some specimens, especially roughness is not so high, we found also subsurface initiation, typical fish eye, you can see. So this is the hardened steel. For the non-hardened steel, and the fracture surfaces looks a bit different. And you see a lot of ridges and also multiple crack initiation. And also you can clearly see that because of the toughness of this material is higher, and the multiple cracks, they propagate and they join together. And you can see also, this is basically the last part on fracture. If we zoom in, and you can also see some features of the surface cracks initiated. But also on the side face, you can see multiple crack again, and some of the crack even severely plastic deformed, and this is due to the last stage that the material is fully apart. Okay, so if we make a cut of those side cracks, and then you find the cracks, of course, this is on the edge specimen, and there are two cracks also here if we make a section. Okay, then let's look at also SN data. First, look at the hardened steel. Then we put together the polished hardened steel of two microstructures. So we want to compare magnetic with magnetic. You can see that, okay, let me just point it out here. We have different markers here, and the field markers corresponding to subsurface initiation with fisheye, whereas the empty markers are those for the surface initiation. So we see actually, indeed, at low stress, and then there are also fisheye initiated, but also at the low stress surface initiation. And we do not really see the difference for magnetic and magnetic for subsurface initiation, if you look at here. But you do see the differences for surface initiation. Magnetic actually have a lower fatigue strength, and this could be related to the lower toughness. And then let's look at also the rough surface specimen. This is magnetic, and then compare again the polished surface with the rough surface, and you can see, of course, with rough surface, then the fatigue stress is reduced and life is reduced as well. Similarly, also for magnetic steel, but we also see that for magnetic steel, the spread is bigger, and this could also be due to, of course, the roughness level is not exactly the same. Could also be due to that magnetic steel is more sensitive to defects or surface defects. Then this is for the non-hardened steels. Here we consider the two conditions, polished and a very rough surface, actually. And you see some difference, actually. The difference is not so significant, meaning that for non-hardened steels, that is much less sensitive to defects. Okay, now understanding that, how to take that into account in the modeling. Several years ago, we proposed a model to describe the fatigue strength prediction based on the fatigue cracker growth. And we think that actually, if we can capture the small cracker growth behavior in different conditions, surface and subsurface, where there is a vacuum condition. If we take that into account and lower a crack growth rate, then we can predict the SN curve. Normally we found in the experiment. So this is some abundance about the model. And so we know that for big crack, and then we can describe that with the stress with the crack growth law. And here we use the Hartman driver more because that can unify the near threshold, but also the last stage of crack growth fracture. What is different from the original crack growth model here is that the threshold and also the KC toughness are not the long crack properties. So they are also dependent on the crack size, meaning that for small crack and then it will be smaller. So this is basically described by the curve here. And then the description of the size dependence of these two parameters is we using the Hartman parameter. And these are the examples showing the model prediction, surface initiation versus subsurface initiation, but with a different size of the crack. And also we compare that with the experiment. That shows quite good agreement, actually, with the published data. So that's for hardened steel. We also apply that to the soft steel or non-hardened steel. Again, we needed to use the crack growth data from experiment. Using the same model, then we find out that we can also describe the SN property very well using this approach, meaning based only on the crack growth data, taking account small crack effect. Okay, now if we use that model to describe the rough surface and we treat also surface roughness as kind of a surface defects, then how do we model the defects? So we know that after the machining, and there are some micro grooves, but also there are some major grooves. So we model major grooves as a kind of this kind of feature like a notch. And of course, material we can consider some very initial defects, which can be very small in the micro size. And then if we make a cut of this this plane, and this shows how we model the defect. So this is basically the depth of the groove, and then there is some initial defects that we can assume. And basically, this equivalent the defect size that we take into account in the model for the solution. Okay, so we say that the model basically can describe this kind of unified SN curve, and that curve is actually bounded with the two limits. And the first limit is very much bounded by the tensile strength and also the fatigue limit. But remember that these two actually are not constant. So the tensile strength is also dependent on the size of defects. So small size defects should be included. And also fatigue limit is also dependent on the defect size. And also we found out that such a curve can be fitted very well with a simple equation here that describes basically these two bounds. And we use this to fit to the crack growth models very well. And so using the mechanical properties of the materials, thresholds, K range, K1C for large cracks, the hardness, and then we determine also these two constants, C and N, and then we can basically using this simple unified model to describe the fatigue strength prediction. Okay, here shows the comparison of the model with experiment. So let's first look at the hardened magnetic steel. Here we only include the surface initiation. And again, we see that for different hardness levels, we see quite a reasonable agreement. Only for the porous one, we see, well, there's some differences. And that maybe is probably due to that these materials, the points, they are not exactly surface initiation. Sometimes it's also related to inclusion of surface defects. Okay, so this is for martensitic. Again, we see that there is quite good agreement between the prediction and the experiment. And for the non-hardened materials, and we see here again, yeah, good agreement, but also showing that the sensitivity of this steel is much less to the defects. To summarize, we have performed the routine bending testing for different different materials to investigate the effect of surface roughness on fatigue strength. And we found that hardened steel is more sensitive to surface roughness. And also for hardened steel, we see the martensitic is more sensitive than compared to the magnetic steels. And we have proposed a unified model to describe the dependence of fatigue strength on the surface roughness, and that seems to give a reasonable, pretty good prediction. So with that, I would like to thank you for your